Welcome to TV Part 2 of the You Can Do video series designed to teach you the basic fundamentals of color television receivers. As you recall, in TV Part 1, you gained an overall view of the various stages required to receive, decode, and reproduce the video image with sound that was transmitted through the air by your local television station. Here in Part 2, we will examine in detail those circuits required to receive and detect the video image and sound. By the time you complete this video, you will have a solid understanding of the UHF tuner, VHF tuner, AFC stage, tuner selection, and the remote control section of the color television receiver. We will begin with the UHF tuner. The tuner section in a television receiver is often referred to as the front end, since it is the first circuit which the received signal must pass through. The function of the UHF tuner stage is to select the desired channel, then convert the selected channel frequency into a lower intermediate frequency value. The UHF tuner is designed to receive channels 14 through 69. As you will soon see, today's modern UHF tuners are very simple devices and very easy to understand. Here you see the block diagram of a typical UHF tuner stage. Notice that it consists of a preselector section, a mixer section, and the oscillator section. The preselector portion of the UHF tuner must satisfy three requirements. First, it must have a bandwidth of 6 MHz and be able to select the desired channel. Second, it must reject all unwanted channels. And third, it must isolate the oscillator stage from the antenna. The primary function of the mixer stage is to combine the RF signal from the preselector section with the RF signal being produced by the UHF oscillator stage. When the mixer combines these two signals, it will output a difference frequency, which will become the intermediate frequency value used by the tuner stage. The oscillator section in the UHF tuner will usually be a Colpitts or ultra-audion configuration. Due to the ultra-high frequencies, special transistors like the silicon epitaxial planar transistor are commonly used in this stage. The operating frequency of this oscillator stage is almost always higher than the RF signal it is being combined or mixed with. The UHF tuner assembly is generally constructed on a separate printed circuit board, which will be contained in a specially designed, shielded enclosure. Here you see a pictorial diagram of a metal enclosure designed for use with the UHF tuner circuit. The heavy lines indicate that the walls surrounding the enclosure and forming the three compartments are somewhat thick. The enclosure is specially designed to reduce the radiation to or from nearby circuits and to maintain frequency stability. The first compartment is where the UHF antenna connects to the stage. This compartment contains the antenna input coil, which looks very similar to a paperclip, the antenna tuned line, which acts as a coupling coil, and a trimmer capacitor, which is gang-tuned with two other capacitors, which form the channel selection circuitry. Notice that the tuned line coupling device is adjacent to an opening between compartments 1 and 2. This window is used to allow the electromagnetic coupling between the two compartments. As you might have guessed, the first compartment is the preselector portion of the UHF tuner stage. The second compartment contains the mixer tuned line, which also acts as a coupling device and is placed physically close to the window between compartments 1 and 2. This compartment also contains a diode, which acts as the mixing device, a capacitor, which is connected between the anode of the mixing diode and the compartment wall, and a coil, which is placed between the anode of the mixer diode and the UHF intermediate frequency output. The second compartment represents the mixer stage of the UHF tuner. The third compartment contains the UHF oscillator circuitry. It is basically a modified form of the Colpitts oscillator configuration called the Ultra Audion. Notice that this circuit uses the silicon epitaxial planar transistor as the primary active component of the oscillator stage. This stage also contains a trimmer capacitor used to adjust the oscillator frequency for channel selection. Also notice the electromagnetic coupling between the oscillator stage and the mixer diode. The capacitors mounted on the metal enclosure are used to reduce unwanted AC frequencies. Now let's see how this circuit works. As the incoming RF signal strikes the antenna, a signal is produced across the antenna input coil. This RF signal is then electromagnetically coupled to the tuned line coil in the first compartment. As you may have noticed, the tuned line coil is in series with the first of 3 gang-tuned trimmer capacitors. The tuned line and the series trimmer capacitor form a tuned resonant circuit. This is the first part of the channel selection circuitry. The selected RF signal is then passed through the window which separates compartment 1 from compartment 2. From here, the signal is electromagnetically coupled to the mixer tuned line coil. Notice that the mixer tuned line coil is also in series with one of the 3 gang-tuned trimmer capacitors. This tuned resonant circuit assures that only the selected channel will be allowed through to the mixer stage. The mixer diode then combines the UHF oscillator signal with the selected RF signal. The selected RF signal is inputted through the coil attached to the anode of the mixer diode. The UHF oscillator signal is electromagnetically coupled to the cathode of the mixer diode. The result of the combined signals is the difference frequencies which are outputted through the UHF intermediate frequency output connecting point. The 2 IF frequencies at the output of the mixer stage are 45.75 MHz for the picture carrier and 41.25 MHz for the sound carrier. You should have noticed that the UHF oscillator stage contains the third of the 3 gang-tuned trimmer capacitors used in the channel selection circuitry. This trimmer capacitor is used to control the output frequency of the oscillator stage and is designed to operate at a frequency higher than the incoming RF signal. The frequency of the oscillator stage is adjusted so that when the incoming RF signals and the higher oscillator signal combine, they will produce an intermediate frequency of 45.75 MHz for the picture carrier and 41.25 MHz for the sound carrier. We will now pause for a short review of the material just discussed. The UHF tuner consists of 3 primary sections. These are the preselector, mixer, and the UHF oscillator sections. The preselector portion of the UHF tuner is used to select the desired channel, block out all unwanted channel frequencies, and isolate the oscillator section from the antenna. The mixer portion of the UHF tuner is responsible for combining the selected RF signals with the signal produced by the UHF oscillator section. The oscillator section of the UHF tuner is designed to operate at a frequency higher than the incoming RF signals by an amount equal to the IF frequency values. The IF, or intermediate frequency values, at the output of the mixer section will be 45.75 MHz for the picture carrier and 41.25 MHz for the sound carrier, regardless of the frequency of the selected channel. This concludes review number 1. At this time, you should stop the video and complete section A in your student workbook. Due to the extreme frequency differences between the UHF and the VHF channel allocations, two separate tuners are almost always required. In this portion of the video, we will concentrate on the VHF tuner stage. The VHF tuner is designed to receive television channels 2 to 13. Here you see a graphic representation of the VHF television frequency spectrum. You should notice a few things about this frequency spectrum. First, there are gaps between channels 4 and 5, 6 and 7, and a large gap between channel 13, which is the last VHF channel, and channel 14, which is the beginning of the UHF band. A portion of the gap between channels 6 and 7 is used for the broadcast of FM radio stations. As you may recall from your You Can Do FM radio videos, the FM radio bandwidth occupies all the frequencies between 88 MHz to 108 MHz. You should also notice that each television channel is 6 MHz wide. This 6 MHz bandwidth is the standard bandwidth for all television channels in both the UHF and the VHF channel frequencies. Channels 2 through 6 are designated as the low-frequency VHF channels. Channels 7 through 13 are designated as the high-frequency VHF channels. Each 6 MHz channel has a picture carrier located at 1.25 MHz above the low-frequency edge of the channel bandwidth. The color subcarrier is located at 3.58 MHz above the picture carrier, and the sound carrier is located at 4.5 MHz above the picture carrier. This places the sound carrier very close to the high-frequency edge of the channel bandwidth. This division of bandwidth is an industry standard for all television channels. Now let's examine the VHF tuner. Here you see a block diagram of a typical VHF tuner. The primary function of the VHF tuner is to select the desired channel, amplify the selected channel, and change the incoming radio frequency signal to a much lower intermediate frequency value. Now let's examine each of these sections and see what they do. The Ballon transformer is used as an impedance matching device between the antenna and the input of the RF amplifier stage. The Ballon transformer plays a key role in reducing the electrical noise caused by the antenna line. Here you see a Ballon transformer with a step-up ratio of 1 to 4. It is called a toroidal coil Ballon. The toroidal coil Ballon is nothing more than a coil wrapped around a donut-shaped core which is made of a ferromagnetic material. The primary advantage of the toroidal coil is that all magnetic flux is contained within the core material. The antenna filter circuit will consist of a series of resonant circuits that are used to prevent undesired signals from reaching the input of the RF amplifier section. This portion of the tuner could be considered as a pre-selector stage, which greatly reduces the interference from undesired frequencies. The tuned circuits in the antenna filter section will be set to resonate at the FM radio bandwidth and associated video IF frequencies. The RF amplifier portion of the VHF tuner performs 4 primary functions. It provides amplification for the weak RF signal, helps provide channel selectivity, improves the signal-to-noise ratio, and overrides any electrical noise which is generated from the oscillator mixer sections. As was mentioned earlier, each television channel has a bandwidth of 6 MHz. The video carrier is close to the low-frequency end of the channel bandwidth, and the sound carrier is very close to the upper end of the channel bandwidth. Therefore, the RF amplifier must have a very broad frequency response in order to provide equal amplification to the entire 6 MHz bandwidth. Since the frequency response of the RF amplifier stage is so wide, the gain of the stage is somewhat reduced. The ideal frequency response of the RF amplifier will be a flat bandpass, which will allow all frequencies falling within this bandpass to be amplified equally. The response of the leading and trailing edges of the response curve will be such that all frequencies falling outside the 6 MHz bandwidth will be completely rejected. Here you see an RF amplifier stage which uses MOSFET technology. The solid-state device in this circuit is an N-channel dual-gate MOSFET design. Field effect transistors are commonly used for RF amplifier stages due to their low noise, high gain, high input impedance, and their stability at very high frequencies. As you saw earlier, the radio frequency spectrum covers a very broad frequency range. Therefore, the RF amplifier stage will only amplify a narrow portion of this entire spectrum. Since the RF amplifier can only amplify a small portion of the entire spectrum, you will typically find a tuned circuit at both the input and output of the amplifier section. The tuned circuits will be adjusted to a limited bandwidth for the amplifier stage. Since the VHF frequency range extends from 30 MHz to 300 MHz in the TV tuner, shielding becomes necessary, wire length between the components must be shorter, component leads must be shorter, intercapacitance in the active components starts to become more of a problem, connecting wires are made larger to obtain a higher Q for the circuit, and LC circuits are replaced with pieces of bent wire or short pieces of coaxial cable. In general, the RF amplifier circuit becomes much more difficult to work with. Since the RF amplifier stage has incoming voltages of only a few microvolts, internal noise, called white noise or random noise, also becomes a problem. The RF amplifier stage must therefore be able to decrease this internal electrical noise while boosting the incoming RF signal to a level sufficient to override this internal noise, which is usually generated by the mixer oscillator circuits. Specially designed FET devices provide the best low noise performance. At VHF frequencies, it becomes very difficult to combine the oscillator and mixer sections in the same shielded compartment within the tuner assembly due to a phenomenon called oscillator pooling. Oscillator pooling occurs when the local oscillator stage begins to synchronize its frequency with the frequencies of the incoming RF signal. If the incoming RF signal and the local oscillator signal synchronize, a loss of reception will occur. This is due to the fact that the intermediate frequency signal will no longer be produced. As you recall, in order to produce an IF signal, there must be a different signal being produced between the two heterodyne signals. Therefore, to avoid the problem of oscillator pooling, the oscillator and mixer stages are almost always contained in separate compartments within the tuner assembly. The oscillator circuit used in the VHF tuner is designed to produce a VHF AC sine wave at its output. The frequency of the oscillator stage will be placed above the incoming RF signals by an amount equal to the intermediate frequencies used by the television receiver design. The amplitude of the oscillator voltage will be many times larger than the RF input signal in order to obtain the maximum conversion gain. As you might have noticed, the Colpitts oscillator configuration is the most commonly used oscillator circuit in the VHF tuner assembly. The gain-tuned coil in the oscillator stage is part of the channel selection circuitry. We will examine the channel selection circuitry later in this video. The mixer stage in the VHF tuner assembly performs the same basic function as performed in the UHF tuner. This stage combines, or heterodynes, the selected RF signal with the VHF oscillator signal to produce the required intermediate frequency signal for the video and sound stages. If the IF frequency of the picture carrier will be 45.75 MHz, the IF frequency for the sound carrier will be 41.25 MHz. These IF, or intermediate frequency signals, represent the difference frequency between the incoming RF signals and the higher frequency oscillator signal. Here you see a simplified schematic diagram of a dual-gate MOSFET circuit being used as a mixing stage. Notice that the inputs for the RF signal and the oscillator signal both contain tuned circuits. Also notice that the output of the mixer stage contains a tuned circuit as well. The tuned circuit at the output will be tuned to the difference frequency between the two signals being fed into the mixer stage. In both the UHF and VHF mixer stages, the difference frequency is obtained by subtracting the incoming RF frequencies from the local oscillator frequency value. This difference frequency then represents the much lower intermediate frequency values. We will now pause for a short review of the material just discussed. The VHF tuner is designed to receive television channels 2 to 13. Each television channel has a bandwidth of 6 MHz. Television channels 2 through 6 are designated as being low-frequency VHF channels. Television channels 7 through 13 are designated as being high-frequency VHF channels. Each 6 MHz channel bandwidth contains the picture carrier, the color subcarrier, and the sound carrier. The standard VHF tuner consists of 5 sections. These are the Bowland transformer, an antenna filter circuit, an RF amplifier section, an oscillator section, and a mixer section. The Bowland transformer is used as an impedance matching device between the antenna and the input of the RF amplifier section. The antenna filter circuit is designed to block all unwanted frequencies from reaching the input of the RF amplifier section. The RF amplifier section is designed to boost the weak incoming RF signal to a level sufficient to override any internal electrical noise which may be generated from the mixer oscillator sections. The oscillator section is designed to operate at a frequency higher than the incoming RF signal by an amount equal to the intermediate frequency value. The mixer section is designed to heterodyne the incoming RF signals with the oscillator signal being produced by the local oscillator section. The mixer section then outputs the difference signal into the video IF detector stage. The difference signal will always be a lower frequency value than either the incoming RF signal or the local oscillator signal. This concludes review number 2. At this time, you should stop the video and complete section B in your student workbook. Up to this point in the video, you have examined the circuits used in the UHF and VHF tuner assemblies. By now, you should have gained an understanding of how each of the various sections contained within the tuner assemblies functions. In this portion of the video, you will examine how the tuner is able to select one channel from the many channel frequencies which are being inputted at the antennas connected to the tuner inputs. Making the tuner stages selective requires that 3 of the sections contained within the tuner assemblies be adjusted simultaneously to the desired frequencies. In the VHF tuner, these 3 sections are the RF amplifier, mixer, and oscillator sections. In the UHF tuner, these 3 sections are the preselector, mixer, and oscillator sections. Channel selection may be accomplished through the use of mechanical means or through the use of solid-state devices. You will examine both types of channel selection devices. Changing channels may be accomplished in one of 2 ways. You can change the inductance of the tuned circuit while leaving the capacitance fixed, or you can change the capacitance while leaving the inductance fixed. It used to be that the most common method was to vary the inductance of the tune circuit through a mechanical means. In today's modern television receivers, however, it has become preferable to vary the capacitance of the tune stage through the means of solid-state devices. We will first examine the older style mechanical tuners. Here you see a drum-style tuner device used for VHF channels. The drum tuner consisted of 13 individual sections which contained the tuned coils necessary to receive the 12 VHF channels, and one section was tuned for the UHF setting. These 13 strips were configured into a cylindrical shape, thus forming the appearance of a drum. Each individual section contained the coils necessary to select a particular channel frequency. As you noticed, there are typically 4 coils for each section. 2 of the coils were used in the RF section of the tuner, 1 for a tuned input and 1 for a tuned output of the RF stage. Another of the coils was used for the oscillator portion of the tuner, and the final coil was used for the mixer portion of the tuner. Basically, the drum switch was designed so that as the tuner shaft was rotated from one channel to the next, a group of tuned coils would be connected to the appropriate circuits within the VHF tuner. Each time the shaft was rotated, a new group of coils would be inserted or connected to the RF amplifier stage, mixer stage, and oscillator stage. Each group of tuned coils would be factory designed and preset to receive one television channel. As you can see, by rotating the tuner shaft, you would be changing the bandwidth operating frequency of the affected circuits, thereby allowing channel selection. Here you see another common mechanical tuning device. It is referred to as a wafer switch. Even though the wafer-style tuner performs the same function as the drum-style tuner, it is considerably different. Notice that each of the 4 wafers contain 13 tuned coils. Also notice that the last 3 coils are wired in series with one another. Each wafer contains the tuned coils necessary to receive and select one channel frequency at a time. The inductance is varied by adding the inductive value of the selected channel when going from TV channel 13 to TV channel 2, or it is subtracted from the value of the selected channel when going upscale from the TV channel 2 to TV channel 13. When the channel selector is positioned on channel 13, the other channel coils are removed from the circuit. And when the channel selector is positioned on channel 2, the total reactance of the circuit will be at maximum since all the coils which are mounted on the wafer are now in series. The first wafer in the wafer-style tuner is used to control the local oscillator section of the VHF tuner. This wafer section generally contains individually tuned coils for the oscillator section instead of the series-connected coils used in the other 3 wafer sections. The mechanical UHF tuners generally used air variable capacitors to perform the task of tuning. The air variable capacitors would have one or more rotating plates for each tuned section of the tuner, and one or more fixed plates for each one of the rotating plates. As the shaft was rotated, the plate area of the capacitors would change in value, thereby changing the operating frequency of the stage the capacitor was connected to. As you can see, the UHF tuner would vary the capacitance of the tune stages instead of the inductance as was used in the VHF tuning devices. Also notice that the UHF tuner only controls 3 stages instead of the 4 stages controlled in the VHF device. The UHF tuner will vary the frequency of the antenna, mixer, and oscillator stages in the UHF tuning device. In the newer television sets, electronic tuning is used almost exclusively, which provides no moving parts within the tuner section. This is accomplished by a special component known as a varactor diode or voltage variable capacitor. Here you see the schematic symbol for this device. As you recall in the You Can Do semiconductor video VT203, whenever a PN junction is reverse biased, a depletion region is established in the midst of the junction. The higher the voltage potential of the reverse bias across the PN junction, the wider the depletion region. This depletion region acts like the dielectric in between two plates of a capacitor. In the case of the varactor diode, the two plates are the P and N type materials. As the reverse bias voltage is increased across the PN junction, the depletion region widens over the PN material. Both PN type materials now have less effective plate area and are effectively spaced further apart, decreasing the capacitance of the device. The decrease in capacitance increases the resonant frequency of the associated tuned circuit. So as the reverse bias voltage increases, the frequency of the tuned circuit increases. Here you see a tuner module utilizing varactor diodes. Notice that the RF mixer and oscillator sections each have a varactor diode to properly tune each stage. Since all three stages must be tuned at the same time, a different form of ganging must be used. With no moving tuner parts, mechanical ganging is out of the question. Therefore, electrical ganging is used. Notice the electrical line connecting the cathodes of each varactor diode. This line is used to simultaneously adjust the capacitance in each stage. Since a specific voltage represents the same capacitance to each of the varactor diodes, all three varactors are a matched set. We will now pause for a short review of the material just discussed. A change in frequency can be accomplished in one of two ways. Either the inductance changes with the capacitance remaining fixed, or the capacitance changes with the inductance remaining fixed. In the older television sets, a tuner drum, composed of 13 sections, would mount a set of tuned coils for each of the antenna, RF amplifier, mixer, and oscillator stages. The channel knob turned this drum to the correct section of coils for each TV channel. The last setting switched to the UHF band of channels. The last three wafers of the wafer switch contained a series of coils wired end to end. As the wafer switch turned each channel setting, more or less inductance would be added to the rest of the tuned circuit. As the channel setting increased, less inductance would be placed into the circuit, which would increase the frequency of the circuit. The first wafer contained individually mounted coils, especially for the oscillator stage. Usually, air variable capacitors were used for tuning through the UHF channels. Each antenna, mixer, and oscillator section consisted of two types of tuner plates, fixed and variable. One or more variable plates was made to rotate parallel to one or more fixed plates to adjust the frequency of its tuned circuit. The varactor diode makes solid-state tuning possible. The varactor diode, or voltage variable capacitor, uses a reverse bias condition to establish a depletion region which acts like the dielectric within a capacitor. The degree of dielectric opposition within the PN-type material changes the capacitive characteristics of the diode. The varactor diode can be placed into a tuned circuit and used to change the resonant frequency simply by varying the degree of reverse bias voltage. This concludes review number 3. Now stop the video and complete section C in your student workbook. In this part of the video, we will examine the automatic frequency control, also known as automatic frequency correction, and take a look at why this stage becomes known as the automatic fine-tuning section. In black and white television sets, the fine-tuning can be out of adjustment by a considerable amount with no apparent lack of picture or sound quality. However, with color TVs, a tighter frequency tolerance is necessary because the color circuits contained in the television receiver require precise tuning. Also, with the advent of TV remote control devices, automatic fine-tuning is a must for consumer convenience. Although the terms AFC and AFT may refer to the same stage, this tighter frequency lock distinguishes the automatic frequency control from the automatic fine-tuning. AFT, or automatic fine-tuning, is basically achieved with the Foster-Seeley discriminator and the varactor diode. As you recall from UCANDO's FM Part 1 video VT402, one of the methods of demodulating FM, or detecting frequency change, is performed by the Foster-Seeley discriminator shown here. In the television system, the Foster-Seeley discriminator is tuned to a higher frequency and receives its input from the video IF amplifier section. When the discriminator detects a rise in frequency, it will output a negative error voltage in proportion to the shift in frequency. If the discriminator detects a decrease in frequency, it will provide an error voltage of a positive proportion. The output of the Foster-Seeley discriminator follows the same basic reverse bias requirements of the varactor diode, but with a reversed and lowered amplitude. A common emitter amplifier is placed in between the Foster-Seeley discriminator and the varactor diode of the local oscillator stage. This amplifier circuit provides inverse DC amplification and the exact bias level required for the varactor diode to correctly offset the drift in frequency. Now, whenever the local oscillator or tuner drifts off frequency, the video IF amplifier will reflect this change, and the Foster-Seeley discriminator will respond by generating an error voltage. This error voltage is inverted, amplified, and adjusted through the common emitter circuit and fed to the varactor diode within the local oscillator stage. Integrated circuits are also used in automatic fine-tuning sections. Here you see an integrated circuit which completely replaces the Foster-Seeley discriminator and the common emitter amplifier circuit. This integrated circuit not only provides error detection through its two differential inputs, but it also provides proper amplification of the error voltage to the varactor diodes. In addition, this circuit may be very precisely aligned to the manufacturer's specifications, even more so than the Foster-Seeley discriminator circuit. In conjunction with the automatic fine-tuning circuitry, some television sets include additional features to help ensure tight frequency specifications. Temperature compensation devices located in the local oscillator stage are used to help stabilize the oscillator from ambient temperature effects. And power supplies are designed to maintain very accurate voltages, which would otherwise cause the frequency to drift considerably. We will now pause for a short review of the material just discussed. Automatic fine-tuning is better able to lock in on the appropriate frequency than the automatic frequency control, which is also called automatic frequency correction. A Foster-Seeley discriminator is sometimes used in the television receiver to detect frequency drift and generate an error voltage in proportion to this drift. Since the Foster-Seeley discriminator outputs a small inverted error voltage, a common emitter circuit is used to reverse and provide the proper amplification of this voltage. Integrated circuits are used in most newer television receivers for detecting, amplifying, and correcting errors in frequency drift. Varactor diodes in the tuner's local oscillator circuit use a correction voltage to maintain a stable operating frequency. Temperature compensation devices and very stable power supplies help ensure tight frequency specifications within the automatic fine-tuning system. This concludes review number 4. Now stop the video and complete Section D in your student workbook. In this portion of the video, we will examine TV remote control, beginning with the transmitting devices. There are two basic methods of transmitting control information from the remote control device to the TV. These are sound and light. The sound method works on the same principle as a tuning fork. Inside the remote control device are 3 aluminum rods. Each rod controls a particular remote control function within the television set. Notice that each aluminum rod is a different length. When any one of the rods is struck, its length will determine its natural rate of vibration, or its resonant sound frequency. The resonant sound frequency of this form of remote control will range from 19 kHz to 45 kHz, which places this acoustic transmitter in the ultrasonic frequency range above human hearing. The control unit works by the user depressing one of the function buttons, which creates tension on the spring. When the button comes to the end of its travel, the spring will be released and recoil, allowing a small hammer to strike the end of the aluminum rod. The aluminum rod thus generates a specific ultrasonic frequency, which the television receiver recognizes as a function signal. After a predetermined time has passed since the function button came to the end of its travel, a silencer is sometimes used in the remote control device to end the vibrational ringing of the aluminum rod. Although acoustic remote control devices, such as this simple mechanical method, are outdated by today's newer electronic technology, they still have one advantage over modern remote control units. No batteries are required. The next logical step in acoustic remote control devices takes an electronic approach. Here you see the circuitry for an electronic acoustical remote control device. This circuit configuration makes up a Hartley oscillator, which can operate at the exact ultrasonic frequencies used by the mechanical remote. The advantage of this electronic remote control is that more direct functions are provided to the consumer than with the mechanical remote. When a function button is depressed, which in this case is actually 2 normally open ganged switches, additional capacitance is placed across the secondary tank circuit of this oscillator by the first half of the ganged switch assembly. This additional capacitance will place the oscillator at a predetermined ultrasonic frequency. The trimmer capacitors in each section provide the service technician a means to readjust the remote control device if any frequency would change. The second half of the switch assembly is used as an on-off switch which only provides power to the oscillator when a function button is depressed. This arrangement conserves battery power and requires no thought on the operator's behalf to turn the remote on and off just before and after depressing a function button. The output of this oscillator is delivered to a special capacitive speaker which has an ultrasonic frequency range. Such a speaker is also known as a transducer. The newer TV remote controls are more compact and use light-emitting diodes which emit invisible infrared light. Infrared light, also abbreviated IR, is just below the frequency range of human vision. An infrared or IR TV remote control will contain very few electronic components. In fact, most of the circuitry used in a modern infrared remote control is built into a single integrated circuit. Each remote control chip has a keypad decoder section, an oscillator or clock stage, a memory circuit which stores digital function codes, a serial pulse output stage, and a power control section. When a function button is depressed on the infrared-style remote control, the keypad decoder section will trip the power on, starting the internal clock, and accessing the memory circuits for the digital pulse code of the chosen function. The digital pulse code is clocked out of the memory circuit and into the serial pulse output stage. The serial pulse output stage assigns a certain timing duration to each binary logic condition within the function code. The serial function code is unloaded from the chip to a general-purpose transistor which drives or switches in power to the IR diode. After this cycle is complete, the power automatically trips off to extend battery life. As you may have experienced, many infrared remote control units will not operate any other pieces of electronic equipment except for the model they are matched to. This is not only due to the various digital codes assigned to each control function by different manufacturers, but also to the different timing rates of binary pulse conditions which various control units transmit. The two major problems a technician will encounter with TV remote controls are low or dead batteries and dirty contacts within the keypad. Both will make the operation of the remote control system seem sluggish or faulty. At this time, we will pause for a short review of the material just discussed. In the older television remote control transmitters, aluminum rods would be tuned to generate a specific ultrasonic frequency, ranging from 19 kHz to 45 kHz. The acoustical electronic remote control uses a Hartley oscillator or similar circuit with capacitance added to select an ultrasonic frequency which is transferred through a capacitive speaker or transducer. Infrared remote control units are essentially digital devices. Inside the IR control unit will be a small chip which controls the transmission of a coded pulse train of infrared light which represents the selected function to the television receiver. This pulse train may differ from other models in the aspects of actual code used, including the bit word length and the timing duration of each binary logic condition. This concludes review number 5. At this time, you should stop the video and complete section E in your student workbook. The final portion of this video will focus on how the television set receives and acts upon the remote control signals. Most modern television sets designed with remote control functions will contain 2 additional stages in the TV block diagram. These are the remote control receiving amplifier string and the decoding section. You will find that the older television sets will contain yet another stage, which consists of an actuator system used to physically move the controls within the television receiver. For example, when ultrasonic systems are used in the older television sets, a transducer will serve as a microphone. A high-gain amplifier is then used to boost the sound picked up from the microphone. If the gain of this amplifier string is set too high, distortion occurs and false signals may trigger one of the unselected functions within the television receiver. In other words, the television receiver may not respond correctly to the command given by the ultrasonic transmitting unit. If the gain is set too low, some of the functions may not work at all. As you can see, the correct gain setting is very important for the proper operation of the remote control system. Now let's see how this system works. The amplified signal travels from the high-gain amplifier string into a decoding section. The decoding section consists of tuned circuits which respond to the proper ultrasonic frequency of that particular remote control function. When one of the tuned circuits is activated by the incoming ultrasonic signal, a voltage will be developed in the series tuned circuit which will activate a power transistor. The power transistor will then drive a relay which will turn on the 110-volt AC motor. Separate 110-volt AC motors and solenoids are then used to physically turn the channel selector, or a small volume control potentiometer contained within the television receiver. Now let's examine another common type of remote control system. Here you see a television receiver which uses infrared light as the controlling source. As you may recall, the transmitter utilizes an infrared diode as the active light source. When the infrared signal reaches the infrared photodetector located on the front of the TV set, it will detect the IR signal and trigger the next stage of the remote control circuit. The photodetector itself may be either an infrared phototransistor or a PIN diode. The output of the IR photodetector is then fed into a pulse shaper circuit which cleans up the incoming IR light pulses and transforms them into a digital pulse string. The digital pulse string is then fed through an inverter which changes the digital pulse string into its binary complement. Next, a series of 6 flip-flops is used so that each bit in the entire digital pulse code may be operated on within the same clock pulse. The binary contents of the first and last flip-flop will identify the beginning and end of each digital pulse string and will help determine if the transmitted infrared signal matches this piece of equipment. When a binary 1 is in the first and last flip-flop, the output of the AND gate will enable the decoding section. The middle 4 flip-flops are used to provide the actual function control code to the decoder. When the AND gate enables the decoder instantly processes the 4-bit function code at its input bus. Based on this 4-bit code, one of the decoder output function lines will be selected for the duration of this clock pulse. Each function line, except the 2 labeled NC, is routed to the next stage within the television receiver. The 2 function lines labeled NC have no connection and represent the output which would be selected if the 4 middle flip-flops contained all binary 1s or binary 0s. This is a built-in feature to help prevent a false function code in the event that a very long infrared light pulse, which was not intended to operate this piece of equipment, reached the photodetector. This long IR pulse, representing all binary 1s, would be shifted into the flip-flops and acted upon like a legitimate function code, when in fact it was not. The circuit scenario just explained is one of many possible methods manufacturers use to decode infrared light pulses. For example, more light pulses may be used in the transmission of function codes, which would require the use of additional registers or flip-flops. The first and last flip-flops in our example were used to pick out what is called the identity bits within the infrared transmission. Some manufacturers may use more or fewer identity bits and may group them together. In fact, the identity bits could be placed anywhere within the infrared transmission. Now that we understand how infrared decoding works within the television receiver, let's couple this with our knowledge of the electronic tuner. As you may recall, the electronic tuner is adjusted in frequency by varying its tuning voltage. In many modern television receivers, a method of stepped tuning is used to place the electronic tuner at the selected TV channel. This is generally accomplished by a digital to analog converter. For more information about digital to analog converters, review your You Can Do Digital 4 video, VT304. The function lines, which are used from the remote control receiver module, are connected to the inputs of a small internal computer. This small computer contains in its memory the programming and data tables required to interpret the meaning of the function line signals and to control certain sections within the television receiver based on these function line signals. Examples would be volume control, channel selection, brightness, and tint settings. When a TV channel is selected, the internal computer outputs the correct parallel data to the digital to analog converter. The digital to analog converter uses the parallel data to generate the voltage level required by the electronic tuner to receive the selected TV channel. At this time, we will pause for a short review of the material just discussed. The ultrasonic-controlled television receiver uses a transducer as a microphone and a high-gain amplifier to boost the ultrasonic signal to a considerable level. A decoder section contains tuned coils which respond to the frequency of each ultrasonic signal. When one of these tuned coils is at resonance, its transistor turns on, which energizes a relay, which supplies AC power to either a motor or solenoid, which is used to change a channel or turn the volume up or down. The television receiver, which is controlled by infrared light, uses a PIN diode or an IR phototransistor as the detecting device. After the light pulse has been cleaned up or reshaped into a more rigid waveform, a decoding process takes place which chooses one of the function lines. A small internal computer is used to output a proper combination of parallel bits to a digital to analog converter. The digital to analog converter supplies a correct tuning voltage to the electronic tuner based on the parallel bits. This concludes review number 6. At this time, you should stop the video and complete section F in your student workbook. Understanding the workings of the modern television receiver is the key to being a proficient television technician. Review your You Can Do videos often to maintain your level of expertise.